Thank you. Hello everyone, it's a great honor to be part of the 70th birthday celebrations of Professor Ramamurthy, his mathematics and his legacy, particularly in mentoring several younger mathematicians. We've been hearing beautiful tributes from his students and mentees, and I thought I'll just say a few things about the India story of this aspect. So I was officially his first PhD student from India. But of course, he has mentored several postdocs before me, as well as many students informally. Some of them, like Rajan and Jyoti Sen Gupta, we would call them the first generation mentees, and some of them are now retired. Only officially, they are very active mathematically. Around the time I graduated, Shauli and Purushottam joined him as postdocs. So we are the second generation mentees. And in a few years, Aksha, Siddhi, and Arpita joined him. These are the third generation, along with students of students, students of postdocs, postdocs of students, and postdocs of postdocs. And we are now soon entering the fourth generation also. And along with the other people that Professor Murthy continues to collaborate with. He makes new collaborations each time he visits India, and he visits India a lot, as we all know. So in addition to the well-known institutions in India, especially around Chennai, the third generation has gone on to build number theory groups in several institutes around India, including the IITs, the Indian Institutes of Science, Education and Research, and the National Institute of Science, Education and Research. He continues to mentor and work with younger people from the fourth generation. And in the next 5 to 6 years, we anticipate that his influence will percolate to many more new IITs, the triple ITs. So the way institutes are named in India is a beautiful topic of study. So IITs, triple ITs, the National Institutes of Technology, NITs, and of course, several upcoming central universities in India. So thank you, Professor Murthy, for your generosity, vision, and deep commitment to the Indian scene. And I wish you many more years of mathematics and mentoring. So now we turn to the mathematical part of the talk. So I wanted to talk today about some central limit theorems in number theory. So the quintessential central limit theorem in number theory goes back to the study of the prime omega function, which is the number of distinct prime divisors of n. So this is an additive function, and using very elementary and neat arguments, we can evaluate the average order of omega of n, and this involves essentially counting reciprocals of primes up to x, and it turns out to be that the average order of omega of n is asymptotic to log n. And this elementary argument can also be used to study average order of higher powers of omega of n. So in this direction, we have this theorem of Turan in 1934, which is a stronger version of the Hardy-Ramanujan theorem on the normal order of omega of n. I won't go so much into the normal order, discussion of normal order, but here is this estimate for the average order of omega of n minus log n square, or omega of n minus log x whole square, as you go for all n up to x. So this argument is also very elementary. You basically open up the bracket, and then you have to focus on looking at the second power of omega of n and evaluate it in a very similar way, but now you have to index over pairs of primes dividing n. So this leads to questions about higher powers of omega of n, and it was Mark Katz who first observed that this can also be understood from a probabilistic perspective. So we can take the following probability space of all the natural numbers up to x and equip it with the discrete uniform distribution. So for any prime p lying in this space, we may define the random variable x sub p as follows. X sub p of n is 1 if p divides n and 0 otherwise. So once we do that, we can talk about expected value of xp, variance, and so on, and then the sums the corresponding quantities for the sums of these random variables. So mu sub p, the expected value of x sub p, turns out to be asymptotic to 1 over p as x goes to infinity. So as our spaces a sub x become larger and larger. And then the variance sigma p square also turns out to be asymptotic to 1 over p minus 1 over p square as x goes to infinity. So these are increasingly behaving like Bernoulli random variables with parameter 1 over p. So we can talk about their sums. Now we don't know whether the xp's are independent of each other in a given probability space, but they do appear to be independent. So if you were to imagine that they are independent, we can talk about the distribution of the sums of these random variables appropriately scaled down by the sums of the expected value and also normalized by the sums of the variance. And central limit theorem machinery will predict the distribution of this normalized quantity here. So in particular, it turns out that if n is in the space a sub x, then the sums of these random variables applied to n is just our omega function. Sums of these mu sub p's therefore is the average order of the omega function. Then sums of the variance also from the expression that we obtained for the variance in the previous slide turns out to be asymptotic to log x. And therefore, machinery of the central limit theorem would predict that this normalized variable omega of n minus log x normalized by square root of log x would be normally distributed. And this was what was proved rigorously by Erdős and Katz. So probability theory predicts these distributions, but they have to be proved rigorously using number theoretic methods. So the Erdős-Katz theorem in 1940 says that as x goes to infinity, this normalized quantity in fact will follow a probability distribution that converges to the Gaussian, the normal distribution as x goes to infinity. Now the good thing about Gaussian distribution is that it is completely determined by all its higher power moments. So an equivalent formulation of the Erdős-Katz theorem is in terms of the rth power moments of this quantity here. And it turns out that as x goes to infinity, these in fact converge to the rth power moments of the Gaussian distribution. So both these statements are equivalent. But to prove Erdős-Katz type theorems, we can just focus on rth power moments of the form mentioned here. Okay, so if we want to extend Erdős-Katz type of theorem to various types of situations, we would start with a counting problem, for example, the average order of an arithmetic function. Check to see if we can interpret or imagine that arithmetic function as a sum of seemingly independent random variables. Then we guess the probabilistic distribution of normalized sums using the machinery of the central limit theorems. And then once we have a guess, we go ahead and prove it with the help of explicit number theoretic methods. So in this context, the Erdős-Katz theorem can be almost immediately generalized to the class of additive functions. And we can also talk about generalization of omega of n to omega of a sub n, where a sub n are integer valued sequences. So general principles for the study of these types of sequences go back to the work of Rammurthy and Kumarmurthy in 1984. And more recently, Rammurthy, Kumarmurthy and Sudhir Pujahari in 2023. And they apply these general principles to a set of interesting sequences, which I'll also tell you about. So for this, we need to quickly set up the notation related to Fourier coefficients of modular cusp forms. So let us take k and n to be positive integers with k even. And let S sub k of n denote the space of primitive modular cusp forms or weight k with respect to gamma naught of n. Let us denote the set of Hecker-Nu forms in this space by f sub k of n. And the cardinality of this set of Hecker-Nu forms is in fact the dimension of the space of primitive modular cusp forms. And one more quick notation, any Hecker-Nu form has a Fourier expansion of this form. So n raised to the k minus 1 by 2 times a sub f of n. So a sub f of n are the normalized Fourier coefficients. So a sub f of 1 is equal to 1, and by the Ramanujan-Deligne inequality, we know that a sub f of p lies in the interval minus 2 to 2 for a prime number p, which is co-prime to the level n. So now what we do is, initially we were considering the probability space of all the numbers up to x. So we can generalize that situation, we can have other analogues. So let us consider the probability space of primes q up to x, and replace omega of n now with omega of these Fourier coefficients on this space. Here we are assuming that our f are, suppose they have integer coefficients. Okay. So Kumar-Murthy and Ram-Murthy derived an Air-Katz type theorem for this sequence that I just told you about, when f is a non-CM Hecke-Nu form with integer coefficients. And this central limit theorem, or an Air-Katz type theorem, is under the assumption of the generalized Riemann hypothesis for Art and L functions. And in recent 2023 work with Sudhir Pujahari, they extend this to a scenario of an Air-Katz type theorem for omega of root q times sums of a sub f of q plus a sub g of q, where f and g are fixed Hecke-Nu forms of the exactly satisfying conditions as above, but of weight 2. And this result is under the assumption of a quasi-GRH for Dedekind zeta functions. So this is a nice generalization of Air-Katz theorem, and it makes us wonder about other types of generalizations. So I'd like to tell you some more things about central limit theorems. Matilde talked about very special central limit theorems in the context of zeta zeros of the Artin-Schreier curves. So I'm going to focus on sequences that are coming from the theory of Hecke-Nu forms. So now we consider the set of Hecke-Nu forms as a probability space. So far we were taking either n's up to x or primes up to x, but now we take the set of Hecke-Nu forms as a probability space, again with the discrete uniform probability. And on this space, for a prime p which is co-prime to the level, we define appropriate random variables x sub p. For example, okay, before I give examples, the question is, so for appropriately defined random variables, can we obtain Air-Katz type theorems? So now this scenario is vertical, right? We are fixing, I mean, we are taking primes, but the probability space varies over k and n. So let us define, for example, x sub p to be equal to, when you apply it to f, this is just the pth normalized Fourier coefficient of f. Now this is an interesting sequence. As we know, this has been very well studied, in particular for a fixed non-CM Hecke-Nu form. The distribution of the sequence a sub f of p is described by the well-known Sato-Tate distribution theorem, which tells you that the sequence is equidistributed with what is often referred to as the semicircle distribution measure, or the Sato-Tate distribution measure. And this distribution theorem has an equivalent formulation, namely, so if you wanted to prove a theorem of this form for any continuous real function, it would be sufficient to prove it for an appropriate, for any sequence of polynomials which contains polynomials of every degree. And in particular, if you were to consider the Chebyshev polynomials, families of Chebyshev polynomials, either of the first or the second kind, the Sato-Tate distribution theorem is in fact equivalent to this neat formulation in terms of the Fourier coefficients directly. So this is this asymptotic or rather the average of a sub f of p to the m as you run over p, all the primes p up to x. This is 1 if m is equal to 0, nothing needs to be done there, but if m is greater than 0, this limit is in fact 0. This is the Sato-Tate distribution theorem. And if we wanted to obtain Air-Katz type theorems for sums of these x sub p's, we have to consider higher moments of these sums of a sub f of p's. Okay, so you take the sum, raise it to the power r, and then study this quantity as you average over the set of all Hecke-New forms of weight k and level n. So one of the earliest theorems in this direction with this kind of a perspective is due to Nagoshi in 2006, who takes, so he needs the weights to grow very fast as a function of x. So that growth condition is encoded by log k by log x goes to infinity as x goes to infinity. I'll tell you why this kind of a condition helps. So if as x goes to infinity, Nagoshi first shows that your Sato-Tate distribution theorem holds on average. So you have the same sum, but now you are averaging over all the Hecke-New forms, not just the non-CM, but in fact all the Hecke-New forms. So this is little o of pi of x. Then we can talk about second moments. So he shows that if you take the square of the sums of a sub f of p, this in fact on average is asymptotic to pi of x itself. So what happens if you now take the square root of pi of x and normalize your quantity here, these sums with square root of pi of x? This leads us towards another Erdős-Katz type of theorem, but now the sequence is different. We are not taking the omega function anymore, but you just have a sub f of p. So the rth power moments of this normalized quantity in fact converge to the rth power moments of the Gaussian distribution. But for this to happen, for now I'm just going to fix a level n and let the weights vary. You need the weights to grow quite rapidly. Okay, and these, by the way, these are the moments here. So for r equal to odd, they vanish, and for r even, these are the values. Okay, so the main technique, as you would have imagined, that would go into Nagoshi's theorem would be about estimates for averages of a sub f of p as you average over all the Hecke-New forms. So this is coming from the Eichler-Selberg-Trace formula. So if you take the terms of the Eichler-Selberg-Trace formula and estimate them, then you get for any c which is greater than 1, you have the following average value of a sub f of p to the m as f runs over all the Hecke-New forms. So this is the main term here is in the numerator you'll have 1 if m is even and 0 if m is odd, and in the denominator you have 1 over p to the m by 2. So now you can take these estimates for the Eichler-Selberg-Trace formula and sum over all the primes p up to x. So in particular for m equal to 2, you would get an error term of the order of log x, and then you have another error term where you have the contribution coming from. So here notice your x is now in the numerator, so you have a very high power of x, and then you have terms coming from the weight and the level. And this is the reason why we need to take our weights to grow very rapidly, because we would want these, we need these error terms to go to 0. So we need our k to grow fast enough so that this whole error term converges to 0, and this is what leads to Nagoshi's growth condition. So it's a very neat and straightforward application of the Eichler-Selberg-Trace formula. Now just some remarks of theorems and ideas related to this. Trace formulas can be applied to obtain equidistribution for families of these Hecke eigenvalues, where you fix a prime p, but now you start varying your spaces of Hecke, modular cusp forms, primitive cusp forms. You can also do this for the space of all the cusp forms. I'm just focusing on new forms for this discussion. So this is due to Serre, but actually this perspective of vertical distribution goes back to the work of Sarnak in 1984, who has had results in the context of mass forms. Okay, so here the vertical equidistribution theorem is that your a sub f of p's are equidistributed with respect to this probability distribution measure mu sub p of t, which as you can see it depends on the prime p. And in a paper around the same time, Conray, Duke and Farmer consider a perspective in which both the primes as well as the weights go to infinity, but the weights should grow suitably faster in comparison to the primes. So if k is greater than e to the p, then the families a sub f of p become equidistributed in -2 to 2 with respect to the original Sartor-Tate distribution measure. So as p goes to infinity, then your mu sub p of t sort of smoothens out into the Sartor-Tate measure. Okay, so and it is this perspective of both primes and k growing in a certain way in relation to each other, which is further exploited by Nagoshi. So his theorem can be, a part of his theorem can be stated in the following way. Let us take I to be a fixed interval in the interval -2 to 2, and let us define mu of I to be equal to the Sartor-Tate measure of this interval I. Okay. So now what we do is we take x sub p, we define the random variable to be equal to the characteristic function of a sub f of p with respect to your interval I, which you have fixed, and let k be growing in such a way that log k by log x goes to infinity as x goes to infinity. So under this condition, a part of Nagoshi's theorem and one of the theorems of Conrad, Duke and Farmer can be stated in this way, that the sums of the expected values of x sub p converge to, are asymptotic to pi of x times the Sartor-Tate measure of mu of I as x goes to infinity. So again, as I had commented earlier, this statement can be interpreted as an averaged out version of the Sartor-Tate theorem. But you need very strong growth conditions for your families. So, okay, the caption is hidden, but this is joint work with my second PhD student, Neha Prabhu. So, we looked at the sequence, these random variables, and we asked questions about higher moments, okay, of the sums of x sub p's. And it turns out that now we need to take stronger growth conditions for k. So as log k over root x log x goes to infinity, as x goes to infinity, we have the following corresponding theorem for the variance of the sums of x sub p of f. So this is asymptotic to, the variance here is asymptotic to pi of x times mu of I minus mu of I whole square. This is again reminiscent of Bernoulli random variables, where the parameters are now the mu of I. And then once you normalize it by the variance, you again have, under these stronger growth conditions, you have the rth power moments of these normalized quantities converge to the rth power moments of the Gaussian distribution. Okay. Okay, and now we were focusing on the characteristic function of our a sub f of p, but we can also consider smooth versions of this theorem, and actually both the characteristic function and the smooth analogues are very closely related to each other. I'll explain that in a minute. So in follow-up joint work with Stefan Bayer and Neha Prabhu, we continued looking at these central limit type theorems, and one of the things that we were interested to do was to, we were wondering if the growth conditions that we had in the theorem with Neha could be reduced or at least brought down to the same level as Nagoshi's theorem. So replace chi-sub I by a suitable test function, and so we take a real valued even test function g in C infinity of R, and then we periodize it in the spirit of the Poisson summation formula. We take a periodized version of this test function, and if your g satisfies suitable conditions, then your g sub L of theta, g sub L of theta is a periodic function and it has a Fourier expansion which would converge absolutely and uniformly, and therefore it can be treated like a nice function. So the Fourier coefficients of this periodized function actually are very closely related to the Fourier transform of the original test function that we start with. So how much time do I have? Yeah, okay, 10. Yeah. Okay. So now under this condition and with these types of test functions, we define the following random variable at p. So define x sub p of f to be equal to the value of our test function g sub L of theta, where theta is now your corresponding angle to your a sub f of p. We had seen before that these lie in the interval -2 to 2. So let theta f of p be the corresponding angle. And as in Nagoshi's theorem, let k be such that log k by log x goes to infinity as x goes to infinity. Then the sums of these expected values will converge to pi of x times the integral of the test function with respect to the Sarto-Tate measure. So this is sort of like the smooth version of the Sarto-Tate distribution theorem, but averaged over all the Hecke-New forms. And then you can also consider questions about variance, and then normalized by variance. The whole machinery goes through exactly as in our previous theorem, but with much better growth conditions. Okay, so we get this asymptotic for the variance, and then when you normalized by your variance, this quantity here, the rth power moments, converge to the rth power moments of the Gaussian distribution. Okay, now we had started with test functions whose Fourier transforms were compactly supported, but now we can loosen that a little bit. So instead of taking compactly supported Fourier transform, let's say the Fourier transform has like an exponential type of a decay, which is encoded by two parameters, lambda and omega, both positive. And under this condition, again, the same kind of asymptotics as above would hold, provided now log k over log of x raised to the 1 plus 1 over omega, where omega is coming from the exponent of absolute of t. If this goes to infinity, as x goes to infinity, then the same type of asymptotic would hold. And now some quick remarks about the proof. Like I said, the study of the characteristic function is closely related to the smooth version. So the idea is to approximate the characteristic function by certain trigonometric polynomials which have nice approximation properties. These go back to the work of Selberg and Berling, and this was also the main idea in the work that the Gaussian, the central limit theorem that Mathilde talked about. So once you do this approximation, you reduce the question about the distribution of the middle quantity into evaluation of moments of this form, where these are these s plus minus of m are coming from the coefficients of these Selberg-Berling polynomials. And then once you have a formulation like this, then you ask questions that go beyond these approximations. Can you talk about smooth test functions of a more general kind and consider the rth power moments of these? Okay, so then the question is about choosing the kind of test functions which will ensure appropriate decay of g of m and the convergence of these moments. So these are the main ideas, and of course evaluating these sums coming from a sub f of p to the m is where we end up using the Eichler-Selberg trace formula. Okay, so some more CLTs. So Neha Prabhu, like she's one of the third generation mentees. So she joined Professor Ramamurthy as a postdoc, and they prove in the very nice paper in which the authors themselves say it has poetic insights related to the central limit theorem. They prove these interesting variants. So they have a CLT for quadratic character sums, appropriately averaged. They have CLTs for quantities which are generalizations of what Nagoshi considered. So a sub f of p to the n, where n is any fixed positive power, which you also adjoin with coefficients of appropriately chosen L functions. And you can also talk about, in the second CLT can be applied to the third one, where you now fix a Hecke eigenform and consider a sub g of p, and you let your f vary when you prove your central limit theorems. So this is a very nice paper to read. Okay, and as I'm running out of time, I'd like to just mention some ongoing joint work with Mohammad Ahmed from the National Defense Academy in Khadakwasla near Pune, and my youngest PhD student Jishu Das, who has just graduated. So we are looking now again at sequences which are coming from the Hecke eigenvalues, but we want our random variables to be parametrized by pairs of primes now. So we now take x of f parametrized by two distinct primes, p and q, and we take the test function g sub l as we had done before, but now we take their values at theta p minus theta q minus theta p plus theta q, and minus theta p minus theta q. This kind of a linear combination really helps us because it reduces the entire study very neatly into explicit Fourier coefficients a sub f of coming from a sub f of p to the m and a sub f of q to the n, for example. So it turns out with these type of random variables now, under the same growth conditions that Nagoshi has, as x goes to infinity, the sums of these expected values as you take pairs of primes, distinct primes up to x, is asymptotic to the square of pi of x times a quantity that now depends on the Fourier coefficients of GL at 0 as well as 1. So in Chantal's talk, we saw some similar quantities coming from level densities of other families. And then this leads to questions about variance. So once we put that, once we take sums of these xpqs, the variance also has a very nice asymptotic. It's asymptotic to the cube of pi of x times this quantity that's now directly coming from the Fourier coefficient of our test function at 1. And our work is ongoing because now, of course, the next question would be to consider higher power moments. It's leading to very intricate combinatorial calculations, which we are working on. So I will just leave this as an open question. For r greater than or equal to 3, do the moments of these normalized quantities coming from these sums of these random variables parametrized over pairs of primes, do these moments converge? And if they converge, do they converge to the Gaussian moments? So this is something that we are investigating. If anyone has any insights on this problem, or if they think this is a wild chase, please let me know. So to quickly conclude, the study of central limit theorems in number theory is a very wide topic. So typically we consider finite families equipped with the uniform probability, and we define appropriate sequences associated to each element in this family, and consider, for example, for a fixed interval I, a counting function that counts the number of elements of the sequence lying in the interval I. And then we try to express this counting function as a sum of seemingly independent random variables, and then we ask questions if one could have CLTs as the size of these families increases. So the kind of families one can talk about are suitable families of curves over finite fields such as hyperelliptic curves, the L covers that Matilde introduced, the Artin-Schreier curves that she talked about, and other types of model families of curves. In different types of aspects, this question has been studied extensively by the work of Katz, Sarnak, Pfeifman, Rudnick, Maosheng Xiong, and Bukul, David, Fagan, and Lalin in one of their projects on the Artin-Schreier curves. I was fortunate to be part of that, and that is the project that introduced me to this beautiful world of central limit theorems. And we also can consider analogous questions coming from families of elliptic curves, y square equal to x cube plus ax plus b, where now you let, just as in the modular forms case, you let your weights vary. Here you let a and b vary in boxes. And we can consider the sequence of the traces of the Frobenius at the primes as we vary over families E of a comma b. So the first moment and the second power moment have been previously studied by Stefan Bayer and Li Zhao. And then we jointly with Bayer and Prabhu, we have central limit theorems for these types of families. So we go to studying the higher power moments. And interestingly enough, eigenvalues of regular graphs have many thematic similarities with eigenvalues of Hecke operators acting on spaces of cusp forms. So one can also talk about distribution of families of eigenvalues of these graphs. They in fact, depending on whether you fix your d or you let d also go to infinity with n, they have distribution measures which are almost exactly the analogues of the Sarto-Tate measure and the vertical measure of Serre. And then Tobias Johnson, I think he was a student of Joel Spencer. In his PhD thesis, he has obtained some central limit type theorems in the context of these families. So I'm pretty much done. One quick question: is there a general theorem from which all of the above CLTs can be derived as special examples? This would be a philosophical theme to think about. And since everyone is sharing pictures, this is a picture that we took yesterday with 6 students, former and current, 7 postdocs, and of course the gentleman who knows him for the longest time. So happy birthday, Professor Multy.
Thank you, Kaneenika. Questions? Online participants, any questions there?